In this video, we will use the following example to learn the method of separation of variables to solve differential equations. Solving differential equations is in general difficult. Usually, we will try to reduce the problem up to a point at which we could use some techniques from algebra, calculus, or ordinary differential equations to solve it. A typical approach is to suppose the particular solution assumes a specific form, then plug in and simplify. There are technically infinitely many ways to assume a specific form for the solution. And the method of separation of variables is one of them, in which we assume the solution has a product form, say u of x comma y equal to capital X times capital Y. Let's carry out the plan. If u of x comma y is equals to capital X times capital Y, then the partial derivative of u with respect to x is equals to capital X prime times capital Y, while the partial derivative of u with respect to y is equals to capital X times capital Y prime. Since both capital X and capital Y depending on only one variable respectively, there should be no ambiguity on what it means by capital X prime or capital Y prime. The next step is to plug in. Hence, we should have du dx plus 3 du dy equal to x prime y plus 3 xy prime equal 0. Or equivalently, we should have x prime y equal negative 3 xy prime. If we divide both sides of these equations by capital X times capital Y, what we left with is capital X prime divided by X equal negative 3 times Y prime divided by Y. Note that the left-hand side of this equation is independent of Y, while the right-hand side of this equation is independent of X. So we should have a quantity that is independent of both Y and X. With this, we conclude that both of those two terms are supposed to be equivalent to a constant denoted by lambda. Upon this, we successfully reduced the partial differential equation problem into a problem of two ordinary differential equations. To continue, we will consider two different cases in accordance to the possible value of this lambda. In the first case, we assume lambda is not equal 0. Thus, the auxiliary equation of capital X prime minus lambda x equals 0 is just r minus lambda equals 0, with the roots given simply by lambda. So we conclude that the solution to this ordinary differential equation is capital X equal to C1 times e to the lambda x. Similarly, the auxiliary equation to the second differential equation is 3r plus lambda, and the root is just r equal to negative lambda over 3. With the solution of this differential equation given by y equal to c sub 2 e to the negative lambda over 3 times y. Since the solution u is supposed to be just the product between capital X and y, we conclude that under this assumption that lambda is not equal 0, the outcome should be c1 times c2 times e to lambda x times e to the negative lambda over 3 times y, or we could simplify the expression by combining those two arbitrary constants into a single one, multiplied by e to the lambda times x minus y over 3. We will continue to study the second case, in which we assume lambda is equal to 0. When that is the case, we should have capital X prime equal to 0, as well as capital Y prime equal to 0. And these two differential equations are particularly simple. All we need to do is just integrate the equation to obtain the solution. Therefore, we conclude that capital X is just the integration of 0 with respect to x, which is in fact a constant, while capital Y is going to be the integral with respect to the variable y. Similarly, the outcome is also a constant. Hence, the solution of the partial differential equation is just the product of capital X and Y, which is just the product of those two arbitrary constants. And we could combine them into a single arbitrary constant denoted by c sub 6. As a common practice, I always suggest my student to figure out some way to check their work after obtaining the solution. For instance, when we are solving differential equations, the best way to check our work is to plug the solution back into the equation and see if our results solve the equation or not. In our problem here, we end up with two solutions. So we could try to plug those two solutions into the given differential equation. For instance, if we plug the first solution into the differential equation, we will end up with du1 dx equal to c sub 3 times e to the lambda x minus y over 3 times lambda. Then the second term is going to be 3 times c sub 3 times e to the lambda x minus y over 3 times negative lambda over 3. Now, with some simple algebraic manipulation, we end up with 0 as the outcome. So we checked the first solution as valid. And you could do the similar thing to the second solution. In fact, in our case, it's even simpler, because the second solution is in fact a constant. So both of those two partial derivatives are just 0. So we just end up with the sum of a bunch of zeros. So the outcome must also be 0. So we have checked our solution and verified that we do end up with some solution of this partial differential equation. And that's the first example in using the separation of variables methods to solve the equation. Thank you for watching. See you next time.